Over the course of our discussions, we have covered several crucial techniques and challenges involved in the construction of Tokyo International Forum. We focused on 5 steps of the top-down method. Additionally, we explore the diaphragm wall construction method, which is crucial for ensuring the structural integrity of the underground levels. We also address the issues of vibration and noise caused by 4 subway lines running near the construction site. To mitigate these problems, we implemented underground anti-vibration walls. The construction utilized existing basement walls on the west side, newly constructed concrete walls on the south and north sides, and earth anchors on the east side. Furthermore, we delved into the placement of vibration isolating pads and the construction wall designed to counteract the risk posed by these vibrations. Our discussions included the use of an underground 3-story reinforced concrete structure with continuous underground walls and the crucial role of the PC bridge in stabilizing the structure against seismic forces and supporting earth pressure. Finally, we discussed the PC bridge connecting the glass hall and the concert hall, which was designed to withstand significant exile loads. It was constructed in 5 detail stages, concluding with the tightening of cables to ensure additional tension and stability. Now that we covered how the preconditions for the construction of the Tokyo International Forum were met, let's move on to how one of the most prominent halls of this building, the glass hall, was built. Initially, Vignoli was hesitant to construct a large glass building in an area prone to seismic activity. After all, glass was not a traditional building material in Japan due to the concerns related to earthquakes. However, Vignoli was keen on realizing a transparent glass hall, despite the technical challenges posed by the building size. Originally, the plan to support the roof with 12 pillars was put into consideration, but the engineering design group later found this approach to be highly inefficient in terms of space utilization. As a result, the design evolved to the current structure, which uses 2 pillars, each 52.5 meters long, spaced 144 meters apart to support the roof. Obayashi, Taisei, and Kajima was involved in the construction of the glass hall, which cost 40 billion yen. This is Team 1, and today we'll present how we address 2 of the 3 issues we discussed: wind pressure and earthquakes. This week, we will review the construction sequence of the glass hall during the top-down phase and discuss how the construction team aimed to address the technical challenges posed by earthquakes and wind pressure encountered during the construction of the glass hall. Before we begin, let us explain how the glass hall is comprised. First, there's a conference block located on the north side of the glass hall. This block consists of 7 floors and serves as a core of the glass hall. Next are the exterior walls of the glass hall. The walls are made entirely of curved glass and are designed to better withstand lateral forces due to their curved shape. Inside the glass hall, there is a cable truss system. 2 cables inside the glass spiral upwards and are located on the north and south sides of the glass hall, supporting the glass against lateral forces. The roof is shaped like the bottom of the ship, which not only enhances the volumetric presence of the glass hall, but also resembles the hull of a ship. There are also cables that transfer the lateral forces from the cable trusses to the main columns. Lastly, the main columns extend from the 4th to the 7th floor on the conference block, resisting the exile load from the roof and the lateral forces from earthquakes and wind pressure. Now, we'll go into detail about the construction process of the glass hall's top-down method step by step. First, the construction started with the main conference room steel structure on the PC concrete slab at the 1st floor level, serving as the core of the entire building structure. Second, for the construction of the large roof, a virtual bench stage was set up at a height of 42 meters above the ground. Third, the main columns, spaced 144 meters apart in a north-south direction, were divided into 17 sections and assembled. Sections 1 through 9 were constructed using a hydraulic crane. For sections 10 to 17, a traveler crane installed on the temporary bend stage was used. Concurrently, the construction of the wall steel structure in the north-south direction was carried out. Fourth, after the main columns were completed, the large roof steel structure was installed by moving 2 traveler cranes from the main columns toward the center over the bench stage. The roof was supported by 44 temporary supports, known as vents, as construction progressed. Eventually, the load was transferred to the 2 main columns using the jack-down method. Fifth, after the jackdown method, the wall steel and the large roof steel were connected, and each cable of the wall cable truss was installed sequentially. Tension was applied to the cables to help the roof resist lateral forces, thereby stabilizing the entire atrium structure. Following this, the installation of the glass walls and the glass roof were completed. Lastly, the vents weighing into a total of approximately 5,000 tons were dismantled, completing the atrium space. This comprehensive approach not only ensured the structural integrity of the glass hull, but also facilitated the aesthetic and functional aspects of its large, transparent design. Next up is the structure and the mechanisms of the truss. The glass hull of the Tokyo International Forum is an expansive atrium space shaped like a convex lens, measuring 210 meters in length and 32 meters at its widest point. To support the glass facade of this hull, a large cable truss structure was employed. This structure embodies the architectural goals of lightness and transparency while also effectively handling loads. The cable truss not only supports lateral loads caused by wind and earthquakes, but also the exile loads from the roof. Let's delve deeper into the structure of this cable truss. The cable truss system is divided into 3 sections across the length of the hull, with each section consisting of multiple units. Here's a breakdown on the components. First are steel mullions. These are resistant to bending and exile loads and are essential in the initial load-bearing process. At the top and bottom of each mullion are steel plates which anchor the unit to different parts of the building, either to roof structure, the conference hall core, or the first floor concrete wall, depending on their location. This anchoring plays a crucial role in load transfer. Second are cables. 2 pairs of cables are connected to the steel plates. The cables bulging inward handle the indoor horizontal loads, and those bulging outward manage the outdoor horizontal loads. These are referred to as positive compression cables and negative compression cables, respectively. Third are steel compression members. Within each unit, there are 7 horizontal compression members that help maintain the arc shape of the cables and transfer stress from the mullions to the vertical cables. Now, let's look at the mechanism by which this cable truss structure resists loads. The first step is load introduction. Horizontal loads from wind forces or earthquakes first impact the glass wall surfaces perpendicular to the wall. The mullions are the primary members that receive these loads and transmit them to the steel compression members. The second step is load transfer. The steel compression members then pass the loads to the arc-shaped cables. Depending on the direction of the external load, different cables receive the stress indoor directed loads go to the positive compression cables, while outdoor directed loads are taken by the negative compression cables. The joints connecting the steel members and cables are ethylene oxide as a friction reducer to prevent load loss, and saddles ensure a pin-connected assembly with the steel members. The third step is load distribution. The load splits along the cables to both the top and the bottom. The load transferred to the bottom first goes into the triangular plate, which is then directed to the foundation, through the conference hall core on the east side, and through the first floor concrete wall on the west side. The load transferred through the top steel plate moves up to the roof structure and is supported by two main pillars, or large columns. The intricate design not only ensures that the glass hull can withstand significant lateral forces, but also beautifully integrates the functionality and aesthetic of the building. To deepen our understanding, let's explore the structure and mechanics of the main pillars in detail. Obayashi Corporation needed to address the transfer of horizontal forces to the transition layer. The roof truss alone was insufficient as it had to directly transfer all horizontal forces to the transition layer. The solution was the implementation of two large columns referred to as obashira. How do the main columns transfer the horizontal forces to the transition layer? The forces are received at the 17th section of the columns where they are tangent to the roof. To prevent the buckling due to these transfer forces, the frame, which thickens progressively down to the 14th section, was designed to resemble a triangle. From the 14th section down to the 11th, the forces travel down each connected layer to the transition space that is linked to the ground. To ensure the complete transfer of forces, high-strength concrete of 80 MPa was used from the 14th to the 11th section. For the lower sections from the 10th to the 1st, where there is less burden of transferring horizontal forces, a relatively lower strength concrete of 30 MPa was used. How were these critical columns that transfer the entire building's horizontal forces constructed? After completing the glass hull cable truss and installing the roof, the main columns were erected. Before installing the main columns, a temporary structure needed to support the horizontal forces in place of the main columns. Obayashi Corporation constructed a temporary vent stage to address this issue, which also facilitated the roof installation and the construction of the main columns. The construction from the 1st to the 9th section involves stacking steel frames with a hydraulic crane and alternating with concrete pouring using tremie pipes. As the construction reached higher levels, the hydraulic crane became impractical, and the traveler crane was used to complete the installation from the 10th to the 17th section. Finally, for additional support against the shore side directional loads of the glass hull, there is a large compression steel member and a W-shaped bridge that both supports the loads and facilitates movement pathways. This comprehensive structural strategy ensures that the glass hull is equipped to handle significant lateral loads effectively while maintaining the architectural vision of transparency and lightness. This concludes our discussion about the construction of the glass hull. Next week, we will discuss in detail the construction process of the roof and how the load was transferred to the main columns using the jackdown method. This was Team 1, and thank you for listening.